Okay, well, welcome everybody to another season of the Western Hemisphere Colloquium in Geometry and Physics. We are fortunate to have Edward Witten of the Institute for Advanced Study. He's going to talk about algebras and entities for black holes. If you have any questions, feel free to just interrupt and ask. Or if you prefer, you can send it to chat, but hopefully there's no need for that. And otherwise, please remain muted while listening. So, Edward, go ahead.
Thanks, Ron, and thanks for the invitation to give today's talk. The title maybe should have been Algebras and Entropies for Black Holes and de Sitter Space. So I'll be talking about the two papers that I've indicated here. But I'll start with a motivating example involving affine Lie algebras. So an affine Lie algebra is a central extension of the Lie algebra of maps from a circle to an ordinary Lie algebra G, which, at least for physicists, is usually simple or semi-simple. Now, if a Hilbert space H is providing a representation of an affine Lie algebra, that means that for every function on the circle valued in the dual of the Lie algebra, there's an operator. If f is the function, I'll call this operator J of f. Physicists write it as the integral over the circle of J paired with the current. So that's the operator that generates the element of the affine Lie algebra corresponding to f. Bounded functions of these operators J of f generate what's called a type 1 von Neumann algebra of all bounded operators on this Hilbert space. However, suppose we take the circle and divide it into two pieces, A and B, as drawn here somewhat crudely. So A and B are just meant to be two intervals into which we've divided the circle. We could consider only functions f with support in, let's say, region A. Then operators J of f for such f generate what's called a von Neumann algebra of type 3. If that's an unfamiliar concept, never mind, because I will explain later what it means. But for now, I'll just say it's not as nice as a type 1 algebra of all operators on a Hilbert space. This is a special case of something much more general that holds in quantum field theory in any dimension. If you're in capital D space-time dimensions, therefore little d equals capital D minus 1 space dimensions, a quantum field theory has a Hilbert space H, and all quantum fields anywhere in space generate the type 1 algebra of all bounded operators on this Hilbert space. But what if we divide space into two disjoint regions, A and B, and consider only operators supported in region A? Then we get an algebra of type 3, generalizing what I said for the affine Lie algebra. This is an old result, originally due to Araki in the 1960s. Now, as a physicist, why would you care about this? The basic motivation, at least for me, comes from black holes. I don't think that was Araki's original motivation. He was just curious about the mathematical structure of quantum field theory. But for our purposes, we'll consider black holes. In this application, region A corresponds to the portion of space that's outside the horizon, causally accessible to an outside observer, and region B is the interior of the black hole, the region behind the horizon. Thus, the operators available to us if we live outside the black hole horizon are the operators in region A. And therefore, the statement is that operators outside the horizon, at least in ordinary quantum field theory, make up a type 3 algebra. However, gravity doesn't fit into the framework of ordinary quantum field theory. In gravity, you can't talk about a definite region of space because space, you don't know what space is a priori. Space is fluctuating quantum mechanically. So you don't know what the whole space-time is. You can't choose a region of space independent of what the geometry is, and the geometry is fluctuating quantum mechanically. So trying to provide a framework that in some sense extends or refines quantum field theory and in which gravity can fit is the main goal in string theory. But anyway, for today's talk, the main point I want to convey is that there are reasons to believe that when gravity is taken into account, operators outside the black hole horizon actually generate an algebra of type 2, not type 3 as in ordinary quantum theory. And this helps resolve some of the puzzles about quantum black holes. Again, I don't want to assume you know what's a type 2 algebra, so I will explain a little bit about that later on. But first, we have to review the idea of black hole thermodynamics, a subject that by now is about 50 years old. Jacob Bekenstein, inspired by questions about from his advisor, John Wheeler, asked what the second law of thermodynamics means in the presence of a black hole. The second law says that for an ordinary system, the entropy can only increase. But if we toss a cup of tea into a black hole, the entropy seems to disappear. Bekenstein wanted to generalize the concept of entropy so that the second law would hold even in the presence of a black hole. So you might, to orient yourself to what he was trying to do, you might think about energy rather than entropy. So Newton had energy, energy was conserved. There was kinetic energy and potential energy, and only the sum is conserved. Energy can be converted between the two kinds. Later, though, physicists learned that there were other kinds of energy. For example, there's thermal energy. When a body slows down and stops because of friction, to claim that energy is conserved, you have to take into account the heat that's generated when the body slows down and the fact that heat is a form of energy. And then there was relativity, E equals mc squared. Rest mass is a form of energy. So energy conservation was retained as physics advanced, but the concept of energy had to be generalized and new kinds of energy were defined. So Bekenstein's idea was that similarly, the notion of entropy had to be generalized so that it would remain valid even in the presence of a black hole. So he wanted to assign an entropy to the black hole in such a way that entropy always increases according to the second law. So your first thought is to find a property of a black hole that can only increase. And you might think that the mass of a black hole can only increase, but that's actually not true. A black hole, for example, could be spinning. And if a black hole is spinning, then when you can make it spin slow down by sending in matter that has opposite angular momentum. And when the spin of the black hole goes down, its mass goes down as well. So it's not true that the mass of the black hole can only increase. But just at this time, Hawking had proved the area theorem, which says that in classical general relativity, the area of the black hole horizon can only increase. So it was fairly natural for Bekenstein to propose that the area of the black hole horizon would represent, in some sense, a contribution to the energy, to the entropy. To be more exact, entropy is dimensionless, but area has dimensions of area, or length squared in 3 space dimensions. So Bekenstein needed a constant with dimensions of area, and well, in units where the speed of light is 1, he proposed that a multiple of the area over Newton's constant times Planck's constant is a contribution to the entropy. So usually I set Planck's constant to 1, but here I've included it because the fact that h bar appears in the denominator in Bekenstein's formula helps explain why black hole entropy is so big in ordinary terms. For example, Bekenstein's entropy of a black hole, if you have a black hole with the mass of the sun, its entropy is 10 to the 20 times bigger than the entropy of the actual sun, according to this formula. While Hawking later, Bekenstein did not know an overall numerical constant in this formula. Hawking later showed that the correct formula is area over 4g h bar. Bekenstein's proposal was that the quantity that satisfies the second law and always increases is not the ordinary entropy of matter and radiation outside a black hole, which I'll call S out, but rather a generalized entropy, which I'm here calling S gen, S generalized, which is the sum of the ordinary entropy outside the black hole plus the area of the black hole over 4g h bar. So that's supposed to be the correct quantity to which the second law applies. And for example, it's not hard to see that when you toss a cup of tea into a black hole, although the outside entropy goes down, this increases by more. To do that calculation, you have to take into account the mass of the cup of tea as well as its entropy. And if you put in actual numbers for a real cup of tea, you'll find that this works just fine. Now, supposedly, Stephen Hawking was skeptical of Bekenstein's idea and set out to disprove it by studying the behavior of a quantum field interacting with a black hole. So what I've drawn here is a Penrose diagram for a black hole. That's a little bit subtle to explain. A Penrose, let me see what I have here. Well, I won't explain it in detail. This is a Penrose diagram is a picture where you schematically show time running vertically and distance from the origin running horizontally. But then Penrose made a conformal mapping to make the picture easier to understand. Anyway, Stephen Hawking studied quantum fields interacting with the black hole and ended up proving that Bekenstein was right by finding that at the quantum level, a black hole is not really black, but has a temperature of order h bar. So I don't really have time to explain Hawking's calculation, and we'll just have to accept the fact that physicists learned half a century ago that the second law really applies not just to the ordinary entropy, but ordinary entropy plus black hole area. Now, for an ordinary system like the cup of tea, the entropy is a measure of the number of degrees of freedom, more precisely the number of degrees of freedom that are relevant under given physical conditions. For example, at a given temperature. Ever since the work of Bekenstein and Hawking, many researchers have felt that somehow the entropy A over 4G of a black hole means that the black hole horizon can be described by some sort of degrees of freedom that live on its surface with 1 bit or qubit for every 4G of area. For instance, in a famous article in 1992, John Wheeler illustrated that idea with this picture. He visualized the horizon of the black hole, a two-sphere, which he divided into little units of area, and he imagined a bit, a 0 or 1, in each unit area. And his idea was that a bit results from measuring a qubit, a quantum bit. Now, as I said, this article was published in 1992. Wheeler had been Bekenstein's advisor, and my guess is he'd been drawing this picture for 20 years. Now, black hole thermodynamics has been spectacularly successful. It turns out that subtle properties of classical general relativity work out in such a way as to ensure that the generalized entropy does behave like a thermodynamic entropy. I already mentioned the most basic example, which is that the Hawking area theorem, which is a fairly subtle fact about classical general relativity, is part of the statement that the generalized second law. The most complete proof of the generalized second law was given relatively recently by Aaron Wall and makes use of Tomita Takasaki theory of von Neumann algebras, which unfortunately I won't have time to talk about today. Other subtle properties of classical general relativity work out in such a way that the first law of thermodynamics is also satisfied, and so on. It turns out, well, there's much more besides, but it turns out that there's a kind of conspiracy where classical general relativity seems to know about black hole thermodynamics. So there's abundant evidence that the generalized entropy does behave as an entropy. But is it the entropy of something? That's been a mystery since the early days of black hole thermodynamics. So Bekenstein just said, think of A over 4G as an entropy. And in the rest of physics, the entropy is the number of degrees of freedom. But we're completely in the dark about what is the number of degrees of freedom proportional to the area of a black hole horizon, which would explain why the area term in the generalized entropy really is the entropy of something. So that's considered the biggest mystery in this field. In what sense the area actually is the entropy of something. And in today's talk, I'm going to explain a slightly abstract and only partial answer. I'll explain that with gravity taken into account, the operators outside a black hole horizon form a type 2 algebra, and generalized entropy is the entropy of a state of this algebra. But first, I'm going to explain a little about the meaning of entropy in quantum mechanics. And then we'll go back to our problem involving gravity and black holes. When we make an observation or analyze an experiment, we're usually studying not the whole universe, but a small subsystem, consisting possibly of the experimental apparatus if it's a lab experiment, or possibly the Milky Way galaxy if we're doing astronomy, or whatever, but usually we're not observing the whole universe. Let me refer generically to the system we're studying as system A and the rest of the universe as B. What happened? What happened was I lost my place. Where were we?
Page 55.
Okay.
55.
Okay. I'm intrigued how you know that so quickly, but anyway. You can explain to me later, but anyway, as I just said, when we make an observation or analyze an experiment, we're usually studying a subsystem, not the whole universe. So I'll generically refer to the system under study as A and the rest of the universe as B. Sorry. So the combined system AB is then the whole universe. Now, usually in quantum mechanics, we assume that each subsystem has its own Hilbert space, HA or HB. And then the Hilbert space of the combined system is a tensor product. So the combined system AB has a Hilbert space HA tensor HB. In such a situation, we can define an algebra curly A of operators of system A. It's just operators on HA. And an algebra B of operators on system B. That's operators on HB. So by definition, these are type 1 von Neumann algebras. A type 1 algebra is the algebra of all operators on a Hilbert space, here HA or HB. Now, the property of a type 1 algebra we'll use is that there's a non-degenerate bilinear form on the algebra given by the trace in this Hilbert space. Now, consider any state of the whole universe, meaning any vector psi, in the combined Hilbert space HAB. We want to define the entropy of system A when the whole universe is in state psi. So we consider the linear function on the algebra that takes an operator to its expectation value in the state. Now, remembering that A has a non-degenerate bilinear form, we see that this linear function on the algebra is the trace of A times rho for some unique element rho of the algebra. It's not hard to show that rho is self-adjoint and non-negative. Moreover, if psi is a unit vector, meaning that its norm is 1, then the trace of rho, which is the trace of 1 times rho, by this formula here, is the expectation value of the identity in the state psi, so it's equal to 1. So any element of the algebra that's self-adjoint, non-negative, and with trace 1 is called a density matrix. So we've learned that any state psi of the whole universe determines a density matrix for the subsystem A. Conversely, if rho is the density matrix, it's not hard to show it's the density matrix of some state psi, assuming system B is big enough. Now, when system A is described by a density matrix rho, its entropy is defined as minus the trace of rho log rho. This is a formula due to von Neumann. It's called the von Neumann entropy. The way he got it was by asking which formula quantum mechanically goes over to the formulas of Gibbs and Boltzmann for entropy in classical mechanics. So Gibbs in particular had showed that the entropy is minus the integral of rho log rho, where rho is the phase-based density. The density matrix is the quantum analog of the phase-based density. The trace is the generalization of the integral. So this is the generalization of classical entropy. It's not hard to prove that S of rho is 0 if and only if rho has rank 1, otherwise it's positive. Under appropriate circumstances, I wrote definitions here, but that was the wrong word. Under appropriate conditions, when thermodynamics is valid, the von Neumann entropy is equivalent to thermodynamic entropy, but it's defined universally, as we just did here, for any quantum state. Now, if rho is a density matrix, then this function has the property that it's positive on an operator of the form A dagger A. So a linear function on algebra that's positive for operators of this kind is called a state of the algebra. A state is called pure if it's not a convex linear combination of other states. It's not hard to prove that rho is a pure state by that definition, if and only if it has rank 1 and equivalently entropy 0. So pure states have entropy 0, and what are called mixed states, which are just states that are not pure, have positive entropy. If rho is a state of system A, which arises as the density matrix of a vector in the combined Hilbert space, it's also not hard to prove that rho is a pure state of system A, if and only if the vector psi is a tensor product of vectors in the two subspaces. Such a psi is called a product state. So system A has 0 entropy if and only if the state of the whole universe is the tensor product of a state of system A and a state of system B, the state psi B of the rest of the universe. That's a possible but atypical state of affairs. Now, the idea that the Bekenstein-Hawking entropy of a black hole should be understood as von Neumann entropy apparently goes back to Raphael-Sorkin in 1983 in a paper that initially attracted only modest attention. The idea was just the following. In a quantum field theory, divide space into two regions, A and B. In our application, as I said, A will be the region outside the horizon, B is the interior of the black hole. Psi is supposed to be a state of the whole universe. And then we tried to define a density matrix rho for the algebra curly A of all operators in region A. In other words, rho is supposed to be the density matrix that describes all experiments that you and I can make, all experiments that you can make as long as you stay outside of the black hole. If you cross the horizon, you could make an observation in region B, but you will have an unfortunate fate. You'd better make those observations quickly because you soon will be crushed into the black hole singularity. As long as you stay outside, rho describes all the observations you can make. So that's a slightly naive formulation. We'll be more critical later. Then Sorkin tried to calculate the entropy minus trace of rho log rho. He found it's infinite. There's an ultraviolet divergence that doesn't depend on the state psi, and the coefficient of the leading divergence is proportional to the area A of the boundary between regions A and B. Well, one might have decided to give up on the grounds that this entropy he tried to define was infinite. But instead of giving up, Sorkin optimistically said that maybe gravity would cut off the divergence so that the coefficient of the area would be not infinity, as he got in ordinary quantum field theory here, but 1 over 4G. And if you like, the logic is that he had done the calculation here without gravity. And if the correct answer is 1 over 4G for the coefficient of the area, then if you try to ignore gravity, which is like setting G to 0, ignoring the gravitational force means setting Newton's constant to 0, infinity is then the correct answer. So Sorkin's hope was that with non-zero G, the answer would be not area times infinity, but area over 4G. That makes a lot of intuitive sense because it matches two ideas. One is that the area over 4G is the irreducible entropy of the system if you live only outside the horizon. And two, the infinity he got, the ultraviolet divergence, was proportional to the area because it comes from short wavelength modes near the horizon, as if the density of the relevant degrees of freedom that give this entropy is 1 degree of freedom for every 4G of area, as in Wheeler's picture. So that was Sorkin in 1983. And there were further developments I won't tell you about in the 80s. The next thing I will tell you about was done in 1993 by Susskind and Uglum. They made a simple observation that strongly supported this point of view. Remember that Bekenstein had defined the generalized entropy, A over 4GH bar plus S out. And to Bekenstein, S out was thermodynamic entropy, and therefore it was only well-defined when thermodynamics is valid, which is not always. But Sorkin had reinterpreted S out as von Neumann entropy, and von Neumann entropy is defined for any quantum state by that formula we had, minus trace of rho log rho. So in ordinary, Sorkin had improved the definitions so that S out would be always defined, but then he had discovered that it was ultraviolet divergence, which was bad. But Susskind and Uglum pointed out an obvious fact that everyone had been overlooking, which is that the first term has the same kind of problem. Because there's an ultraviolet divergence in the relation between the bare Newton constant G0 and the physical observed Newton constant G. When Hawking had done his calculation to demonstrate that Bekenstein supposedly was correct, he didn't include quantum loops that normalized Newton's constant, so he worked with the bare Newton constant G0. But when we interpret this formula in the real world, we'll presumably have in mind the physical Newton constant G. The relation between the two involves an ultraviolet divergence. And Susskind and Uglum showed in the leading approximation, but this was extended later by others, that the divergence in 1 over G precisely cancels the divergence in S out. So the generalized entropy is better defined than either term is on the right-hand side. So 21st century developments have strongly supported these ideas, though leaving plenty of mysteries. And as I've told you in the available time, I'll just talk about one aspect of the story. Why is it that that entropy is better defined when we include gravity? In other words, the entropy of the region outside the horizon is ill-defined in quantum field theory. So S out had that quadratic divergence that Sorkin had pointed out. But the generalized entropy is well-defined. In other words, apparently the entropy of the region outside the horizon, which we think is the generalized entropy, is well-defined once gravity is included. So I'm going to give a slightly abstract answer to this one question. But maybe I'll stop for questions before going on to do that. First of all, as I already explained in ordinary quantum mechanics, when we consider a system AB made from subsystems A and B, we usually assume at the start that each system has its own Hilbert space, HA or HB. And then if the combined system is in a state psi AB, the density matrix of system A generically has a high rank and a positive entropy, But if psi is a product state, rho could be a pure state density matrix with zero entropy. Thus, in ordinary quantum mechanics, whether a subsystem A of a larger system AB has a positive entropy or not depends on the choice of the state. Depends on the state. So in ordinary quantum mechanics, most states have positive entropy, but some states have zero entropy. Generic psi has positive entropy, but product states have zero entropy. That's not the situation for the entropy of a region of space in quantum field theory. In this picture, Sorkin had obtained an ultraviolet divergence in the entropy. The leading ultraviolet divergence does not depend on the state. Every state looks like the vacuum at short distances. So the leading divergent term of the entropy is the same as it is for the vacuum, regardless of the state. And therefore, the entropy of any state is plus infinity. Well, the root of the problem is that it's not true in quantum field theory, that there are separate Hilbert spaces, HA and HB, for outside and inside regions. There's only a combined Hilbert space H for the whole system. What the separate regions A and B have are not Hilbert spaces HA and HB, but only algebras of observables, curly A and curly B. These algebras act on H, so they can be defined to be von Neumann algebras. A von Neumann algebra is just an algebra of operators on a Hilbert space, closed under weak limits. So simply because the algebras in region A or region B act on the Hilbert space of the whole system, we can regard them as von Neumann algebras. There are broadly three types of von Neumann algebra. A type 1 algebra is the kind we're familiar with, even if we don't use the terminology. It's the algebra of all operators on a Hilbert space. In ordinary quantum mechanics, when we discuss the system A, it has a Hilbert space, HA, and the algebra of observables is the algebra of all operators on this Hilbert space. One can define density matrices and entropies for such a system. We actually did so already. And there are pure states that have zero entropy. Remember, a density matrix is just a positive matrix of positive self-adjoint operator of trace 1. And if it has rank 1, that corresponds to a pure state of zero entropy. The other types are less familiar. So in other words, zero entropy means that the density matrix is the projection operator onto a one-dimensional subspace of HA. The other types are less familiar, but first I'll state the bottom line. A type 2 algebra does not have pure states, but it does have density matrices and entropies. A type 3 algebra is the worst type. A system whose observables are type 3 algebra does not have pure states and also does not have density matrices or entropies. By now, you may anticipate the bad news. In quantum field theory, the algebra of observables of a region of spacetime is always of type 3. So to a region, you can never associate a pure state or a density matrix or entropy. You can think of the type 3 nature of the algebra as the reason for the universal ultraviolet divergence of the entanglement entropy. However, it turns out that including gravity in a semi-classical way changes the picture. It changes the algebra of the region outside the horizon from type 3 to type 2. So when gravity is turned on even semi-classically, the region outside the black hole horizon is described by an algebra in which the notion of entropy is well defined, though there is no notion of a quantum mechanical microstate, a pure state of the algebra. We can interpret that as a somewhat abstract answer to the question of why including gravity enabled us to convert the ill-defined S out into the better-defined generalized entropy. Turning on gravity turned to type 3 algebra, where entropy is not a natural notion, into a type 2 algebra, where entropy is well-defined. But to understand how this works, we need to know something about von Neumann algebras of type 2 and type 3. A type 2 algebra was originally constructed by Murray and von Neumann as follows. First, what I'll call a qubit is just a quantum system with a two-dimensional Hilbert space. Let A and B be systems consisting of countably many qubits. Keeping only n qubits first of system A and n more of system B, we consider a state where the nth qubit of system A is completely entangled with the nth qubit of system B. If you don't know that terminology, I've arranged a state psi whose density matrix is a multiple of the identity. So I've picked psi. The key property of the state psi is that if little a is an operator in the algebra that acts on HA, that means little a only acts on the qubits of system A, not on the qubits of system B. Then the expectation value of A in the state psi is a multiple of trace A. The coefficient is actually 2 to the minus n. So I've picked a state that would make that true. I've used the fact that 2 to the minus n times the identity is a positive operator of trace 1. And every such positive operator of trace 1 is the density matrix of some state of the combined system, and I've simply picked a state that makes that true. So let A and A prime be operators that act only on system A, but I'll specify, since system A really has infinitely many spins or qubits, I'll specify that there's a finite set of them, let's say the first K, in which A and A prime act. And now we define this function f of A, which is the expectation value of A in the state psi. But as I've just told you, I've arranged so that that's a multiple of the trace of A. I'm on a call. Okay. Since it is such a multiple, you see that f of A prime is equal to f of A prime A, because they're both equal to 2 to the minus n times the trace of A prime. And the coefficient 2 to the minus n ensures that f of 1 is 1. So the trace, I should say, is the trace in the Hilbert space of system A, ignoring system B. Now, if A is any operator that acts only on finitely many qubits or spins of system capital A, then f of A is defined and independent of n as soon as n is big enough. In other words, as soon as we include all qubits in which A acts. So the function f of A has a large n limit. When n goes to infinity, the function f of A can be defined for any operator that acts on any finite set of qubits in system A. And of course, it still satisfies these relations. And it's also positive in this sense, because that was true for every n. So far, we've defined f on the whole algebra A naught of all operators that act on only finitely many qubits of system A. By taking weak limits, you can compute A naught to a von Neumann algebra curly A that now acts on a separable Hilbert space, still with the function f of A with the same properties I've stated. And because of this relation, that function is usually called a trace, but it's not the trace in any Hilbert space representation. It's a trace with a factor 2 to the minus n removed. So it's 2 to the minus n times a trace. Sorry. Well, it's a trace with the infinite factor 2 to the plus n removed, or a vanishing factor 2 to the minus n subtracted, added. So we've constructed a von Neumann algebra, an infinite von Neumann algebra with a trace. Now, there's a more elementary example of an infinite dimensional algebra with a trace, the type 1 algebra B of all operators on an infinite dimensional Hilbert space curly H. But in this example, while we can define a trace, it's not defined for all elements of B, only those that are trace class. For instance, the identity element of B does not have a trace. By contrast, from the infinite system of qubits, we constructed an algebra curly A in which every element has a trace. So clearly, it's an essentially new type of algebra. In fact, it's the simplest example of a type 2 algebra. It's the type 2-1 factor of Murray and von Neumann. Factor just means that its center is trivial. Its center consists only of complex scalars. Factor is the von Neumann algebra analog of a simple Lie group, for example. Small generalizations of this construction lead to algebras of type 3. We just modify the previous construction a little bit so that the density matrix for each qubit is not a multiple of the identity. Any generic state will do, but this is an example. For this state, the density matrix is this 2 by 2 matrix. So it's positive and it's invertible, but it's not a multiple of the identity. Everything I said before is still true, except it's not true. The only thing which is not true is that it's no longer true that f of a prime equals f of a prime a. So we can still take the large n limit and define an infinite algebra, but this infinite algebra does not have a trace. What we get this way is an algebra of type 3. In contrast to algebras of type 1, algebras of type 2 or 3 do not have an irreducible representation in Hilbert space. Whenever such an algebra acts on a Hilbert space, it always commutes with another algebra of the same type. For example, we constructed our type 2 and type 3 algebras as algebras of operators on the A part of a two-part system AB. So in that construction, they commute with an identical algebra that acts on system B. The difference between type 2 and type 3 is that a type 2 algebra has a trace and a type 3 algebra does not. Moreover, in a type 2 algebra, the trace is non-degenerate in the sense that the trace of AA prime, which I'll write this way, is a non-degenerate and positive definite bilinear form on the algebra. That follows from the positivity condition. So if f of a is any linear function on the algebra, it's the trace of a times some a prime in the algebra. So now let's go back to the situation considered by Sorkin. We consider some state psi of the whole universe. Suppose it were true that physics in region A is described by a type 2 algebra, curly A. Then the linear function that takes an operator to its expectation value in the state psi would be equal to the trace of A times rho sub A for some element of the algebra that I'll call rho sub A. That would be true because every linear, as I said a couple slides ago, back here, every linear function is the trace of A times some A prime. So in particular, this kind of linear function has that property. And I've just written rho A for what I called A prime previously. In the case of ordinary quantum mechanics, that means for type 1 algebra, this condition is the definition of the density matrix rho A of the state psi for measurements in region A. So it makes sense to call rho A the density matrix also in the type 2 situation. And once we have density matrices, we can define entropies as well. So if the region outside the horizon is described by a type 2 algebra, then we can define an entropy for this region. Now, as I've already remarked, in ordinary quantum field theory, the algebras associated to regions are of type 3. So entropy is then not a good notion. But it turns out that when we include gravity, things are different. Gravitational effects, no matter how small Newton's constant is, as long as it's not zero, convert the type 3 algebras into type 2 algebras. The mathematical mechanism leading to this is quite simple and not at all new. It goes back to Kahn and Takasaki in the 70s. What's new is only that this mechanism is actually implemented by gravity in the field of a black hole. The details are different in the two cases. The two cases are the black hole and cosmology. I didn't actually talk about cosmology, but I might say a word at the end if there's time. I'll only have time for very brief explanations. But before I talk about the black hole, I'll just say that what were Kahn and Takasaki doing? Well, type 3 algebras are difficult to study. But it turns out that if A is a type 3-1 algebra, which turns out to be the generic type of a type 3 algebra, then there is an associated type 2 infinity algebra, A hat, that can be canonically constructed from A and from which A can be reconstructed, essentially. So what Kahn and Takasaki were doing was trying to study type 3 algebras. And they learned that relating a type 3 algebra to a type 2 algebra was useful for studying type 3 algebras. Now, in this project, we're not really trying to study type 3 algebras, but we're stuck with the type 3 algebra. We'd be better off if we had a type 2 algebra. It turns out that when you include gravity, the Kahn-Takasaki mechanism is implemented, and the type 3 algebra is converted to the type 2 algebra that they use as a tool to study the type 3 algebra. So that's what I'm going to tell you in the last little bit. Well, first I'll explain their definition. Suppose that A is a von Neumann algebra. It acts on a Hilbert space H with a cyclic separating vector psi. So cyclic means that, well, separating means that A psi is not zero if A is a non-zero element of the algebra. And cyclic means that vectors of the form A psi are dense in the algebra. So you can always assume that A acts on a Hilbert space H with a cyclic separating vector. Then there's something called Tomita-Takasaki theory that to an algebra with a cyclic separating vector associates what's called the modular operator of the algebra for that vector psi. And then let H be minus log delta psi. Well, what Kahn and Takasaki do, okay. The group of unitary transformations generated by H, the group of unitaries of this form, is called the modular automorphism group. Abstractly, it's isomorphic to R. So in this situation, there's a group of automorphisms. Okay. The main theorem of Tomita-Takasaki theory says that these unitaries do generate automorphisms of A. So A has this modular automorphism group that depended on the choice of psi. But Kahn and Takasaki showed that if you take what's called the cross product of the algebra A by its modular automorphism group, that cross product does not depend on psi up to a canonical isomorphism. So to state it with the cross product very briefly, you replace the Hilbert space that A acts on by the Hilbert space tensored L2 of R, where you think of L2 of R as the space of square integral functions of a new real variable x. Then you define the cross product algebra, which is the von Neumann algebra generated by A and bounded functions of H plus X. So you literally just brutally take the sum of H plus X acts on L2 of R, H acts on the original Hilbert space, so the sum acts on the combined Hilbert space. Then you consider, to get a von Neumann algebra, you consider bounded functions of H plus X, And the von Neumann algebra generated by the original algebra plus those bounded functions is called the cross product. And even though the definition appears to depend on psi, Kahn and Takasaki showed that up to a canonical isomorphism, it does not. It depends only on the algebra. So, and moreover, they showed that this cross product is a type 2. So what made it useful was that it's a type 2 algebra canonically associated to the type 3 algebra, and from which the type 3 algebra, moreover, can be reconstructed via what's called Takasaki duality. So, well, it has many remarkable properties, some of which I've mentioned. Well, here's one, I have mentioned this. The definition used the vector psi, but the algebra you make is independent of psi up to a canonical isomorphism. And moreover, if you start with the type 3-1 algebra, as in quantum field theory, then what you get is a type 2 infinity algebra. And there's an explicit form, so as a type 2 infinity algebra, it has a trace, and there's an explicit formula for the trace function on the algebra. So to get from ordinary quantum field theory, where we can't define entropy, or we can define it and say it's plus infinity, to gravity, where we can define it and get a finite answer, we just need to know that gravity adds one variable to the construction of the Hilbert space, namely what I call x, and one generator to the algebra of operators, namely h plus x. So it turns out that that's what happens, but I'll have to be very brief in explaining it. I've drawn what's called a Penrose diagram of the maximally extended Schwarzschild black hole in an asymptotically flat spacetime. So the black hole maximally extended has two asymptotically flat worlds, a world outside the horizon where we might live, and a behind the horizon second world. And for our purposes, the two systems A and B are going to be just the region on the two sides of the black hole, here and here. And the black hole itself is a wormhole that connects these two asymptotically flat universes. The extra operator that's accessible to us, in other words, the operators who live out here, and that corresponds to what I called h plus x in defining the cross product, is HR, the ADM energy measured at infinity on the right side. If you're not familiar with the ADM energy, then just think of it as energy. In general relativity, the energy is defined at spatial infinity by a formula due to Arnold, Deser, and Misner. So what I called h plus x is just the energy measured here, and what I called x is the energy measured way down here. For the cyclic separating vector psi, we can take what's called the Hartle-Hawking state of the black hole. And the modular operator delta psi of this state is known from classic results. And up to a constant beta, which is the inverse of the Hawking temperature, the modular Hamiltonian is the difference between h right, which is, remember, h right was h plus x, and h left was x. So gravity, because of this formula for the modular Hamiltonian in the field of the black hole, gravity, okay. What gravity does that we can't do in ordinary quantum field theory, in ordinary quantum field theory, you have to measure the energy by a bulk integral. With gravity, you can measure the energy at infinity. And in particular, there's the ADM energy that you can measure here. You could also have measured the energy here. They're different. One of them I've called h plus x, one I've called x. In ordinary quantum field theory, to define the energy, you'd have to integrate over all of space. And then it would receive contributions on both sides of the black hole. So what gravity does for us, in ordinary quantum field theory, we'd have the operator h. But with gravity, we can separate h, the total energy, as something measured at infinity on one side, minus something measured at infinity on the other side. So gravity is making the operator h plus x accessible to the observer on the right side outside the black hole. As a result, the algebra of observables for this observer is not the type 3 algebra A that you'd have in ordinary quantum field theory, but is the cross product algebra A hat of type infinity. That gives a framework for interpreting black hole entropy. It's just the entropy of a state of the type 2 infinity algebra. There's a similar story for cosmological horizons. That's the topic of the second paper that I mentioned at the beginning, but I won't talk about it now. So thank you. In summary, I've tried to explain how physicists became convinced that incorporating gravity makes entropy better defined than it is in ordinary quantum field theory. And then I've tried to give at least a few hints of a slightly abstract explanation involving von Neumann algebras and cross products and so on, of why that's actually true. Thank you very much.
Thank you very much, Edward. Let's just, yeah, people can raise their hand and go sequentially. So Greg, would you like to start?
Yeah. So if I think about our dense matter colleagues and an experiment that they're doing maybe with cold atoms and Bose-Einstein condensates and so on, then you know, they will describe their experiments in terms of states. For example, they'll talk about the state of a Bose-Einstein condensate, and they'll even measure the entropy of these states.
Yes.
On the other hand, I think that those experiments should be explained and ultimately explained in terms of quantum field theory, like QED or maybe the standard model if we're more careful. So on the other hand, I would think that only the operator algebra inside that laboratory would be really relevant, and certainly quantum gravity should not be relevant.
Yeah.
So how is that compatible with the fact that type 3 algebras don't have states and entropies?
Well, a pragmatic answer is that you didn't have to use the full quantum field theory for what they're doing. So a simplified operator algebra, which is actually of type 1, is sufficient for analyzing the Bose-Einstein condensate, the cold atom problem.
But ultimately, I mean, it should be described in terms of the standard model.
If you want to do it in terms of the standard model, you will have difficulties, but you'll have to justify the idea that entropy differences make sense rather than entropies. The standard, if you really, it's not going to be a useful way to analyze that problem, but if you want to analyze that problem using the operator algebra, the standard model, you will indeed have difficulties because it's of type 3. You could save a lot of trouble if you're willing to put in an ultraviolet cutoff or something and give yourself a type 1 algebra. You're asking to do things the hard way, definitely.
No, it's just a matter of in principle, but okay, thank you.
Sure. Jeff seems to be next.
I guess let me, hi Edward, thanks for the nice talk. At the beginning of the talk, you showed a picture due to Wheeler of a event horizon of a black hole with I'm hearing a lot of noise, I'm not sure why.
Someone has to be muted. Try that.
Anyway, okay, you showed a picture of a black hole due to Wheeler with little degrees of freedom blocked on the horizon of the black hole. And then at the end, you showed that coupling to gravity changes the algebra from type 3 to type 2.
Yes.
It's kind of a vague question, but does that fact support that picture in some way? In particular, it kind of looks from the picture like you have a finite dimensional Hilbert space.
Yes.
But my understanding of type 2 algebras is that they're associated to infinite dimensional Hilbert spaces.
Yes, the picture is trying to get a type 1 algebra. So for type 2 algebra, entropy makes sense, but we do not have microstates. So we believe that ultimately a black hole has microstates. And Wheeler's picture was trying to motivate thinking about the microstates. So I'd say we're a long way from having in the rather modest contribution I made in this lecture. We're a long way from having type 1 and microstates. So no, we haven't justified Wheeler's picture. There are some things that do work, though, that I didn't really have time to explain. I explained why we had a type 2 algebra. So entropy was well-defined. But we'd like to know that it's not just well-defined, but agrees with the Bekenstein-Hawking, well, the formula due to Bekenstein and many other people who refined it, A over 4G plus S out. So I didn't have time to explain that. So all I did was to say why we can define entropies. But if you, so important limitation of the work that I didn't explain is that there's an additive renormalization constant in this definition of entropy. So what we define are really entropy differences. For any one state, we can't define the entropy. The reason we can't is that there's no canonical normalization of the trace. You could rescale the trace, it would still be a trace, and the entropy of any state would be shifted by log C. Up to an additive renormalization constant, you can show that the entropy of a state of the type 2 algebra agrees with the generalized entropy when that's defined. The generalized entropy is only defined for semi-classical states. So this is, in the second paper I mentioned at the beginning, and also in a third paper we're writing, this is explained, but I didn't have time to explain it in the talk.
Okay, thanks.
Sure. What's the next question? Go ahead.
Well, I have my hand up if I can.
Yes, please.
I was wondering, is the trace that you're using related to the Dixmuir trace that Kahn talks about?
I don't know enough about what Kahn does, but it's the only trace there can be on a type 2 algebra.
Yeah, like it's a trace that can be infinite, but it still satisfies trace AB is equal to trace BA.
When it's defined.
Yeah.
It can be. Okay. In what I explained in the lecture was a type 2-1 algebra, which is the trace is less than infinity for all A. I think I forgot to say something I'd meant to say. If we take the all operators on a Hilbert space, that has a trace, but the trace of the identity is infinite. So only operators of trace class have traces. Then we could define a third algebra. I think I forgot to define it in the lecture, which I'd been meaning to. A tensor B. It's said to be of type 2 infinity. It has a trace. You see, both the algebras A and B have traces, so C does also. But because the trace in B is only defined for some elements, the same is true for C. So C is an algebra of type 2 infinity, which is the right kind of algebra for the black hole. I did not have time in the lecture to talk about de Sitter space or cosmology. But for that application, the important algebra is a type 2-1 algebra. So you're mentioning a trace that's only defined for some elements. Maybe Dixmuir was talking about a type 2 infinity algebra, but from the little, I don't know, so I can't answer the question really.
Okay, thanks.
Sure. There's another question about Victoria.
Hi. So my question is actually about, let's say, there is a Rita-Kanagi proposal for
Yes.
entropy, right? And
Yes.
I'm a kind of quantum physicist, but with special in theoretical physics, but I'm really interested in simulations of a space-time, like, emergence of space-time via quantum error correction codes. And that's like what people do at Stanford. It's like it from qubit. It's like, well, it was it from bit by Wheeler, but now it's it from qubit. So my question is related to de Sitter space, because I was talking to some physicists, And we have some problem with because we don't have DS CFT correspondence yet, as it was explained that there are some boundary conditions not defined for de Sitter space. But in ADS CFT, we have this, in ADS CFT, you have this correspondent, right? So we have this Takanagi proposal. So we actually can connect entanglement. Like, what is Rea Takanagi proposal? It's a formula, it translates quantitative entanglement in the boundary theory into a purely geometrical quantity, right? We connect this quantum mechanical entropy with geodesic bulk. So space-time and quantum field theory, and we're connecting all of this. So can we, I understand it's not like technically related to this type 2 algebra, but you mentioned entropy and like qubits and all of this. So can we also define this proposal, yet the boundary conditions are not defined for, and there is no kind of correspondence, DS CFT yet?
Well, there are a lot of questions there all at once. It's true that quantum de Sitter space is not as well understood as quantum anti-de Sitter space, because there's no equally good analog of the ADS CFT correspondence of that duality. That's one true fact. Since you mentioned work at Stanford, Lenny Susskind has been trying to define a dual, an example of a dual. I'm not sure, well, it's hard to know how, if the proposal will work. Ryu Takanagi is a generalization of the Bekenstein story I talked about in the lecture. However, what I said about the black hole is hard to generalize precisely to the Ryu Takanagi setup. Ryu and Takanagi are in a case where the entropy actually is divergent, because the boundary theory does have a type 3 algebra. So, okay.
Yeah, but
yeah,
I understand it's all open questions, but well, it's like your intuition maybe, since can we get this correspondence? What do you think eventually?
I think all I can tell you is that I hope that the sort of thing I talked about could be extended to shed light on some of the questions you're asking about, but it hasn't been done yet. So I can't give you definite answers, unfortunately. Good questions, though.
Thank you.
I see another person with hands up, Arkadas.
Hi, I feel like this question is probably about a baby prerequisite for this talk rather than the actual content of the talk. But I'll ask it anyway in case I don't know, in case you have a quick answer. So if we have space-time as a finite discrete space-time, and if we have two pieces A and B, in that full set of states would be the tangent product of the states of A and B. So somehow in taking this limit of finer and finer grid, that turns out to not work anymore?
Yes, that's correct. Your statement is not entirely correct, because even on a finite grid, if you had a gauge theory, you would not have the tensor product. But you're correct that for many theories, like scalar theories, there would be a tensor product structure if you had a finite grid. But that tensor product structure is lost in the limit of a continuum theory.
Do you have like a quick intuitive thought about what makes it not work in the continuum limit?
Well, look at the example I gave. All that's important is that the continuum limit has infinitely many degrees of freedom. So when I explained the Murray von Neumann type 2-1 algebra. So we had, let's say AN, an algebra, Hilbert space or algebra acting on n qubits, or let me call it HNA. So a Hilbert space of n qubits of system A, and then we had n qubits of system B. It was completely factorized. Then we took the n to infinity limit. I skipped a couple steps, but we took the n to infinity limit. The function f of A had a limit. And so we defined an algebra. I didn't quite define the Hilbert space, which was of type 2-1, as it turns out. I didn't quite define the Hilbert space at X1. The sort of approved way to do that is with the GNS construction. But maybe there isn't quite time to explain it now. For every finite n, there's a factorization. But as n goes to infinity, there's not. You won't find a simpler example than this. I've actually written a couple articles where I explain this example. The one I'd recommend more was written just last fall, and it's called Why Does Quantum Field Theory in Curved Spacetime Make Sense? And What Happens to the Algebra of Observables in the Thermodynamic Limit? So that article is my attempt to give an elementary explanation of the answer to your question. Whether you'd like it or not, I can't say, but you can look at it if you want.
I'll check it out. Thank you very much.
Sure.
Jacques?
Yeah, I think I missed something. In defining the cross product, you had a Hilbert space H hat, which was H tensor L2 of R.
Yes.
And the Hamiltonian was the modular Hamiltonian H plus X. But X, the spectrum of X is the whole real numbers.
Yes.
But in the application to gravity, you wanted to replace X by the ADM energy, whose spectrum is, of course,
Yes.
positive numbers.
Yes.
Does the whole thing go through if I replace L2 of R with some other space, or like L2 of R plus or something?
Well, that's a great question. And of course, you're drawing attention to a few of the things I tried to sweep under the rug. So I'll get back to the black hole in a second, but I do want to mention that in the case of type 2-1, we actually did have L2 of R plus. And that was why we got type 2-1 instead of type 2 infinity. For the black hole, we look at states close to a black hole of some mass. Better, we should say that the black hole has a fixed size, and that means its mass is, let's see, Gm over R. So its mass is the size over G. We keep the size fixed, and we're working asymptotically near G equals 0, so the mass is going to infinity. And what I call X is really the black hole mass relative to some fiducial mass that we start with. So it's a renormalized mass. X is really, to say it more accurately, ADM on the left minus R over G, where R is the radius, short-shell radius of the black hole we start with. It might be a little bit too much. It's hard to dot all the I's and cross all the T's in giving a quick answer. But because there's a subtraction involved, X is unbounded above and below. Now, if we had a better model where we could look at black holes not near some fixed mass, but of arbitrary mass, then you'd be right, and X would be unbounded below. And actually, in a forthcoming paper with Pennington, in a simpler model where we can look at black holes of all mass simultaneously, it'll be more like X being bounded below. But then, although there's a type 2 infinity algebra, it's not a simple cross product. It's your question definitely drew attention to some of the gaps in what I explained, and it's a little bit hard to fix it properly.
But it will be fixed in the forthcoming paper.
Well, it has been fixed in the previous papers in the sense that I could, even in the first paper from last December, which was on the black hole, if you look at that paper, you'll find, I don't think you'd have the question you asked if you looked at that paper, but in trying to present the lecture without assuming much background, I cut a lot of corners, and it's hard to fill in the missing steps right now. There's another paper to appear, well, with Chandrasekhar and Pennington. There's another paper which also answers your question for the black hole more elegantly than in the original paper from last December. I'm not sure if I should stop here or try to say any more in answer to your question. I'm tempted to say one little thing.
Or to the organizers.
In this discussion, you start with some state, which is the thermal state at some temperature. The temperature, or equivalently the size of the black hole, is kept fixed, and we work asymptotically near G equals 0, so the mass is very big. Then we're allowed to add or subtract any amount of energy of order 1. It can be arbitrarily big, but it's independent of G. So the energy can oscillate above and below its starting value by any amount, but the starting value is of order 1 over G. Any amount, but an amount of order 1. So okay. That's the best I want to try to do right now, I think. There were too many compromises where I left things out at various points, so that it's hard to do better in answering your question right now.
Thanks.
And we move to the next person, Krishna.
Krishna, go ahead.
You are muted, maybe?
Well, maybe, I don't know if he's still there. Nash has another question. Why don't you go ahead?
No, I haven't. My hand should have been taken down. I haven't done it.
Okay, fine. Well, unless Krishna has a question, it looks like there aren't any more.
Okay, so let's everybody thank Edward for the beautiful talk. And the next talk will be in 3 weeks, I believe, because of the holidays. We'll send out the announcement.
Okay, thank you very much.
Thank you very much.
Thanks.
Thanks.